So this is our final bit in the nomenclature chapter and on naming. If we go through our naming chart that we've gone through the type 1 compounds, which were the ones with one combining capacity. So those are the type 1s. They're ionic compounds, a metal and a non-metal, but there's only always the same cation, right? So it stays the same. Type 2 were the metals with more than one charge, so usually the transition metal, so more than one charge. And those we had two different ways of naming. We had the stock naming system, which is the Roman numerals in brackets after the cation, and then we had the Latin system, where it was the Latin base name ending in either ic or us, depending on the combining capacity used. The third kind that we talked about were non-ionic, so these were two metals together, and so they were the ones that we didn't talk about the common ion formed or combining capacity, and they're probably the most literal. The trick about these ones is recognizing when you're in this system, and so these are our bonds between two non-metals, so things that are beyond the step, to the right of the step, and we go through that, and they're really the literal ones. So sulfur trioxide, dinitrogen trioxide, phosphorus pentachloride, and going back and forth in those ones was pretty literal, honestly. After we did that, we did the polyatomics, and the polyatomics go by the type 1 and the type 2 naming conventions. They are back to the ionic compounds, but they are not binary compounds. They have more than two elements in them, and you have a table in your package here to help name those polyatomics. And so they were a little bit trickier to recognize. When you see the formula, you see there's a whole lot more here in the compound. And we're not talking about sulfide. Sulfate is different. 8 hydroxide is a tricky one. Same with cyanide, chlorite. So it's about using your resources and becoming familiar with them. So we're going to go on and name the last kind, the acids. And there's two different kinds of acids. We get to name acids that have no oxygen in them. And the classic would be HCl, or hydrochloric acid. Or we could name acids that have oxygen in them. So typically it's that anion. We're back to the polyatomics. So oxygen containing acids have a different system. And if they are, well, they end in either ite or ate, then they have us or ic. And I'm going to go through the notes here and explain that one. So let's go back to these. So acids have hydrogen as the cation, and the anion is either a single anion or a polyatomic. Acids are always dissolved in water, and so after every formula, you will always write AQ. They don't display the properties of acid unless they are dissolved in water, they are a solution, and so it's important that that AQ goes at the end. That's what it means. It's a dissolved in water. It's an aqueous solution. So acids that contain no oxygen, the example of this is HCl, or hydrochloric acid, is the one that I use because oftentimes that's something that you're already familiar with. And so I think these table numbers are wrong in the notes here, page 7 and page 8, but I think you'll find them. There are rules on, whoops, sorry, wrong one, on here about how to name ones that have no oxygen, ones that have oxygen. The other thing that's in your formula pages, and this is a bit of a cheat, but it is a table here of some common acids. And so these ones would not be the ones with no oxygen and the ones that do contain oxygen. So no oxygen and oxygen. Don't know why I tried to write with the mouse there. It doesn't work so well. I'll go back to the pen. Let's go back to the notes. So here we have hydrochloric acid, why that's there, would be H as the cation and Cl. H is H plus, Cl is minus. These are back to ionic substances, and so we can use the combining capacities. Hydrosulfuric acid, so always H as the cation as soon as you see the word acid, or AQ after. And then sulfuric, what we're talking about is sulfur as the anion. So sulfur would have a 2 minus combining capacity, or -2. So making the formula for this would be H2 S. Whoops, sorry, and I'm forgetting something here. My goodness, I said it was a big deal, and then I didn't do it. So it would be AQ at the end, and AQ at the end. Okay, let's keep going. Hopefully I don't miss something like that again. Hydrocyanic acid, so hydrogen as a cation. Cyanic is relating to the polyatomic that does not have oxygen in it, so cyanide. And they would combine to make an electrically neutral compound as HCN aqueous. That's hydrocyanic acid. So non-binary compound, but still a non-oxy acid. These ones, when we name them, when you see there's no oxygen there, the name is going to start with hydro. And then it's the root word of your cation ending with ic, so bromic acid. Here you can see in the notes they're given as aqueous after, because that's important when we're talking about acids. So this one would be HI, it's very friendly, hydro. The I is iodine, so it becomes iodic acid. I put a bit of a space between these, but technically there shouldn't be one. So HF would be hydrofluoric acid. I tried not to leave the space in that one. So those are the non-oxygen containing acids, and those are the ones that are listed at the top. Sorry, I'll go to the right place here. In this really information-rich space up here. Those are the examples and such that you're given. Okay, so let's go on to the other kind, the last kind of acids, and the last bit of our nomenclature. So these are oxygens that contain acids. They still have hydrogen as the cation, always the same, and they have oxygen in them. So we're dealing with the polyatomic. So we talk about the root word of the anion, and it's basically, so, if it's sulfate, it becomes sulfuric acid, and if it's sulfite, it becomes sulfurous acid. So these are a little bit hard to remember. The way I remember this is that sometimes after you ate something, you feel icky. I don't know. Again, it's not in the notes, but I put it in the videos and I teach it like that, so it's something you can remember. And the other end, the us, is ite. So I just remember this one. When you eat something, sometimes you feel icky, and that's the way that I remember this. I'll try and model that as I go through these ones, because it's literally the way I do it. So sulfuric acid, so as soon as you see ic at the end here, it doesn't start with hydro, so now we're in the world of oxy acids, or oxygen-containing acids. So sulfuric acid, if you feel icky, that was because you ate something. So we're looking for sulfate, right? That's the go-between here. And so for sulfate, I'd look up the sulfate anion. It's SO4 2-. And so I always have hydrogen as the cation. My pencil's a little bit messy here. If I make this electrically neutral, I'd have H2SO4. Oops, it keeps wanting to, that looks like a 9. It's not a 9. We'll try that again. The pen's a little jumpy on me. 4. AQ. Sorry, that's so messy. Let's try another one. So nitric acid, and again, as soon as I see the ic, that means that I'm talking about the polyatomic nitrate. And nitrate is NO3-. I would put that together with my hydrogen cation, and so that would be HNO3 aqueous. When I crisscross those up or make it electrically neutral, it's a 1-to-1 ratio. Sulfurous acid, so as soon as I see us, it is the ite part, so sulfite is the polyatomic I'd look up, and so I would have sulfite, so that's SO3 2-, and again with this it's hydrogen as the cation, so making it electrically neutral, I'd have H2SO3 aqueous. All right, so going the other way with these takes a little bit of dissection to go through and see what is in here. So if I pull them apart into the ions, we'd have hydrogen ion and PO4 3 minus. It did that 4 thing again where it looks like a 9. I'll try and leave a little bit more space. And so PO4 3 minus is phosphate. And sometimes after you ate something, you feel icky. So this would be phosphic acid. Another one here, this polyatomic is acetate. So we'd have hydrogen as the cation and C2H3O2 as the anion. So that's acetate. Another example of after you ate something, you might feel icky. So this would be acetic acid. And I'm guessing that that's something that you've heard of, acetic acid. Okay, so next one, H plus and NO2 negative. NO2 negative, looking that up on the polyatomics, that would be nitrite. So that would make this nitrous acid, not nitric acid, because that's a different polyatomic in there. I think a lot of this is something that just takes practice. You'll note that we did acids here, but no bases, because bases, this is just a bit of an aside here, bases in our discussion often are hydroxides. So that was in the polyatomics. And there's not a separate system of nomenclature for bases. I would encourage you to give a lot of practice to this. You'll notice that there's quite a bit of practice in the assigned questions and the review, but maybe a more fun way to do it would be the activity that comes up next, so the bingo activity. Yeah, it's really about understanding your resources, understanding what information is in the periodic table, how much information is in your formula sheets, but also how to utilize that information.